Okay, so we are going to get lots of practice with hypothesis tests for means on this. Plus, we'll get a little practice with binomial distributions and variance and standard deviation. I know, some of your favorite problems. One thing I struggled with was question number 1. I knew it had to have t, but got stuck when distinguishing which one was right. And where are the numerators and the square root in question 1 squared? Okay. So first of all, let's go ahead. You can see that we're requiring a standardized test statistic. So let's read the problem. A researcher believes a new diet should improve weight gain in laboratory mice. If 10 control mice of the old diet gain an average of 4 ounces with a standard deviation of 0.3 ounces, while the average gain for 10 mice on the new diet is 4.8 ounces with a standard deviation of 0.2 ounces, what is the p-value? So first of all, we need a standardized test statistic, which is our statistic minus the parameter, and divided by the standard error of the statistic. And I'm pulling this straight from your math chart. It would basically be, you take the standard deviation for the first sample, square it over n1, plus standard deviation for the second sample, square it over n2. So we know that x old minus x new is 4 minus 4.8, which is basically 0.8. There's our old standard deviation, there's our new. And also we need to know what our hypothesis is. Our null is that there is no difference, whereas we think that the old one has less weight gain, so we think it is less than 0. So let's go ahead and calculate the t test statistic. Why is it t? Because we're dealing with means here, not proportions. So we have 4 minus 4.8, that's the difference, and then minus 0, all over square root of 0.3 squared over 10 plus 0.2 squared over 10. And that basically matches choice A. And you can see that it says less than. In fact, all these say less than. So they have the right direction for the alternate hypotheses. Number 2, same diet, different numbers. Okay, we've got 12 mice on the new diet is 5.3 ounces of weight gain and a standard deviation of 0.5. And then 15 control mice have a weight gain of 5 ounces on average with a standard deviation of 0.4 ounces. What is the p-value? So we know that our x new minus x old is 0.3, our standard deviation for the new and the old, and our hypothesis is there is no difference. And we are thinking that the difference is actually greater than 0, that we gain more on the new diet. And then the degrees of freedom, if we're using conservative values, we take the smaller of the 2 samples and subtract 1, so we use 11. So our standardized test statistic, just like we did before, we will do t is greater than 5.3 minus 5 minus 0, because our difference, our hypothesized value is 0, that there is no difference, right? And take it over our standard deviation with the equation, and we get 1.690 with degrees of freedom of 11. And we get 0.0596. And remember, this is the same formula we just used in the last problem to calculate the standard error. So the p-value, using TCDF, with this value and those degrees of freedom, we get 0.060, right? And we can also use technology to give us the p-value. So I'll show you technology here. Okay, since we have the t-test statistic, what I'm going to do first is I'm going to use the TCDF to show you how to calculate that probability. Hit enter, it's going to ask you for your lower and your upper. Since we want greater than 1.690, I will put that in the first one, and then for the upper we'll put infinity, or as close as we can get to it on this calculator, 1e to the 99. We have 11 degrees of freedom, and then we hit calculate, and we get 0.0595, or about 0.06, all right? Now there's another way to do this. You can hit stat, we're going to do test, right? And we're doing a hypothesis test, 2 samples and a t-test. Hit enter, and we have stats, and our first sample average is 5.3, and the standard deviation for that is 0.5, so I'm putting the new data in first. And then the old data, the old mean is 5, and the old standard deviation is 0.4. Oops, I got to put sample size. Sample size for the first one is 12. Sorry about that. And then we'll put in the old mean, which is 5, and the old standard deviation, which is 0.4, and the old diet was 15 mice, so I'll have 15. And then our alternate hypothesis is that this difference of new minus old is greater than 0. So actually, I'm just saying that the new is higher than the old. So I hit enter there. So it doesn't really do a 0 thing here. You're just comparing the first mean and the second mean. We never have pooled, and then we hit calculate. And voila, there is your probability, 0.0529. Now, a cool thing you can also do with this, hit stat test. We're going to go back to that 2 sample t-test, and we already have everything entered. There was another option down here besides calculate, and that's called draw. If you hit enter, there you go, ignore that box plot. It actually shows a nice little drawing with your 0.0529. So, nice little extra. So one thing I want to mention on that previous one, you'll notice the p-values were different. That's because when I calculated it, I used the conservative degrees of freedom here. So here we're getting closer to 0.06. But when you use technology, it will use a much higher value for the degrees of freedom, which it calculates automatically. Number 3, a fast food chain advertises that their large bag of French fries has a weight of 150 grams. Some high school students who enjoy French fries at every lunch suspect that they are getting less than the advertised amount. With a scale borrowed from their physics teacher, they weigh a random sample of 15 bags. What is the conclusion if the sample mean is 145.8 grams and the standard deviation is 12.81 grams? All right, so we're looking at evidence. We're going to have to run a hypothesis test. So I'm going to include all the steps to the hypothesis test. First of all is state. What is my null? That my true mean is 150 grams, and my alternate is I'm worried that it's less than 150 grams. And I define mu. Mu is the true mean weight of all large bags of French fries. Assume a significance, now I could say that restaurant or that chain if I wanted to be more clear. Assume a significance level or alpha of 0.05. If they don't give you anything, use 0.05. Our plan is we're going to use a 1 sample t-test for mu once our conditions are met. Random. It is given that the bags are randomly selected. If you look up in the problem, they weigh a random sample. Don't say it's given if it's not there, but don't say it's assumed if it is there. So make sure if it says it, say that it's there, okay? 10% condition. So we need to make sure we didn't use more than 10% of fries, which means we need at least 150 bags of fries, and that seems very reasonable for a fast food chain, all right? Then finally, the large normal. Now, we don't know the population distribution. We don't know if it is normal, but n is less than 30 and we're not given the data. So that's kind of a problem. But it seems reasonable to assume that there is no strong skew or outliers in the bag of fries because it probably would be pretty obvious. They probably have a scoop that's roughly the same size. Now, onto the calculations. We need to do our test statistic, and here's our data, right? And we'll just substitute this in. Remember that we have 145.8 is our sample. 150 comes from our hypothesis. This is the standard deviation for our sample, and we divide by square root of sample size. So we get a test statistic of negative 1.27. Our degrees of freedom is 15 minus 1, which is 14. Since we have a test statistic, we'll go ahead and first calculate the p-value using that. Second distribution, it's a t distribution, so it's TCDF. And we're looking at less than negative 1.27, so we have negative 1e to the 99. Then we put negative 1.27. And our degrees of freedom is 14 because our sample size is 15. And we get a p-value of 0.1124. We can also do this using stat test and go a t-test basically, because we only have one sample. Make sure we're in stats, and we have our mean value, hypothesized value for fries is 150. Our mean from our sample is 145.8. And then our standard deviation for our French fries is 12.81. And we took a sample of 15 French fries. And our alternate hypothesis is that our bags are lighter than 150. And if we go down here and draw, you can see that the p-value is 0.1124, and there's your test statistic. I'll go ahead and run it without the draw. And you can see there it is. So we have our p-value of 0.1124. Since our p-value of 0.1124 is greater than typical alphas of 0.05 and even 0.10, we fail to reject H0, because it's not that surprising then. So the students do not have sufficient evidence to reject the fast food chain's claim. The correct answer is D. Number 4. In a random survey of 500 women, 315 said they would rather be poor and thin than rich and fat. In a random survey of 400 men, 220 said they would rather be poor and thin than rich and fat. Is there sufficient evidence to show that the proportion of women who would rather be poor and thin than rich and fat is greater than the proportion of men who would rather be poor and thin than rich and fat? Okay, so we're going to have to compare two proportions, right? And so I'm going to go ahead and do the whole structure like I did before on problem 3. So state is, my null hypothesis is that the difference between them is 0. Like there's no difference between men and women. My alternate is, I think more women, a higher proportion of women, would rather be poor and thin than rich and fat. And in fact, it tells that to you where it says, is there evidence that it is greater right here? Okay. And then I define what P1 and P2 are, where P1 is a true proportion of all women who would rather be poor and thin, and P2 is a true proportion of all men who would rather be poor and thin, and then I list my alpha of 0.05. So this is a 2-proportion z-test, and there's my 2 sample values. And then I can go ahead and calculate. It's very important to pool these together. So we take our successes from sample 1 plus sample 2, and our total sample size for sample 1 and 2 combined, and I get a combined proportion of 0.594. All right, so that's not to be confused with P1 hat or P2 hat. This is combined. Using that value, I calculate a standard deviation, and I have 0.0329 if I want to go ahead and calculate a Z value. We'll also check conditions, which I can fit in here. So random, both surveys are described, it says random survey of 500 women and random survey of 400 men. So both surveys are described as taken randomly. 10% condition, 500 is definitely less than 10% of all women, and 400 is less than 10% of all men. Finally, large counts condition, which I'll do up here. So for sample 1, remember, use your combined proportion. Don't use the individual sample. And calculate your successes and your failures. And you can see that all of these are easily above 10, so our conditions are met. So then we can get to the nitty-gritty of the math. So again, here are all our values. I'm going to go ahead and calculate my test statistic, and I get 0.63, which is for the females, minus 0.55. And that difference, the parameter for the difference should be 0 divided by 0.0329, and I get 2.432 and a p-value of 0.0075. So first we'll go ahead and calculate the probability since we have our z-score, second distribution, normal CDF. And we want probability that it's greater than 2.432. And that goes all the way to infinity, which for this calculator is 1e to the 99. We're using a mean of 0 and a standard deviation of 1 because we're using z-scores, so we're on the standardized normal curve. and we get 0.0075. Now let's go ahead and do this using the calculator function for a 2 proportion z-test. So we come down here, stat test, 2 proportion z-test, and we know that on our first sample we had 315 out of 500. For our second sample we had 220 out of 400. Our alternate hypothesis is that proportion 1 is greater than proportion 2, since we believe that P1 minus P2 is greater than 0. And we'll just go ahead and draw it. And you can see the p-value is 0.0076, very close to what I had. And let me go ahead and just do it the old-fashioned way. 2 prop z-test. Enter and make sure you're in, well, it's only stats, and we hit calculate. And you can see now that it pretty much matches what we got, 0.00756, really 0.00756, even though they have 0.0075. So because our p-value is less than the alpha of 0.01, we reject H0. There is very strong evidence that the proportion of women who would rather be poor and thin than rich and fat is greater than the proportion of men who would rather be poor and thin than rich and fat. Remember, the first sentence that we do is always saying, what is our p-value? And we compare it to alpha. All right. So our p-value is 0.0075. That's less than 0.01. We reject H0. And although we could have used alpha as 0.05, honestly, so either way, we're rejecting H0. The second sentence is, do you have evidence or do you not have evidence? Because if we have a very low p-value, this is very strong evidence, and the evidence is always for the alternate hypothesis. And so your answer is B. And I guess that's probably why I use 0.01, because it's up there in the sentence. Number 5. A linear regression analysis relating secretary salaries to years of experience yields y hat equals 19.78 plus 2.405 times x, y hat being predicted y, where x is years of salary and y experience and y is salary in thousands of dollars. Which of the following is the most proper conclusion? So they say a starting secretary will earn $19,780. All right. First of all, and then it talks about one with 70 years of experience. So you see a very bad word in stats, will. So that's definitely not the answer. And in addition, if someone has 70 years of experience, they are 90 years old. Hopefully they're retired. All right. This is extrapolating, not a good thing. B, starting secretaries average $19,780 with bonuses of $2,405 every year. No, that's probably actually a raise, not a bonus. All right. There's a cause and effect relationship. We can never determine that just based on a linear relationship. We need to do an experiment for cause and effect. And then for D, starting salaries for secretaries average $19,780 and each year of experience associated with an average extra $2,405. That makes sense. And then finally, E, they said there's high correlation. Well, there's no way to infer the correlation. We only have the equation. We have no idea how good the fit is. So the correct answer is D. Number 6. A 2008 survey of 500 households concluded that 82% of the population uses grocery coupons. Which of the following best describes what is meant by the poll having a margin of error of 3%? Well, it's 82% plus or minus 3%. This gives us the range of plausible values. So from the low end, it could be anywhere from 79% to 85%. So it's likely that we did capture the true value somewhere in that range. All right, all of those are plausible values, so the correct answer is E. 7, for an advertising promotion, an auto dealer hands out 1,000 lottery tickets with a prize of a new car worth $25,000. For someone with a single ticket, what is the standard deviation for the amount 1? So we're going to create a probability distribution. And this is like from your random variables unit, chapter 6, unit D, your favorite, I know. So we have only two outcomes. Either you won nothing, and that would be 999 of the 1,000 tickets, or you won the car, and that would be one of the tickets. And we're going to calculate standard deviation the old-fashioned way. You should be prepared to do that. So first of all, we need the mean, which you pulled from the math chart. And then if I go ahead, what that means is I'm going to multiply every outcome by its probability. So let me show you what I mean there. So see that x of I, that's your outcome. And then that p of x of I, that's your probability. So I got to go 0 times this plus 25,000 times that. And I get 25. So then I can go and calculate standard deviation. Now I'm going to do variance instead of standard deviation right away, just so I don't have to use the square root. So variance, I'm just going to look at adding up all the differences between the outcomes and the expected value. So 0 minus 25, square it, times its associated probability. And then 25,000 minus 25, square it, times its associated probability of 1 over 1,000. Number crunching, we get the variance is 624,375. Take the square root of that for the standard deviation, and we get $790.17. Now here's the faster way to do a probability distribution, especially since we only have two outcomes. So I'm going to go stat and then hit edit. I'm going to create a list. So my first outcome is 0. My second outcome is 25,000. And then I need to go ahead and put in the probabilities. We've got 999 divided by 1,000, which we know is 0.999. 1 divided by 1,000 is 0.001. Then we hit stat, calc, one of our stats. Now, one thing we're actually going to do in here is we're going to put in a frequency list. So we don't normally do that. Second list. List 2 had my probabilities in it. Then hit calculate. And what you'll find interesting there is your 790.17. It does not do a sample standard deviation because we have a probability distribution and the probabilities add up to 1. So it just skips that altogether. So that is the super fast way to calculate standard deviation. So I would recommend this if doing multiple choice problems. Number 8. A company selling home appliances claims that the accompanying instruction guides are written at a 6th grade reading level. An English teacher believes that the true figure is higher, and with the help of an AP Stat student, runs a hypothesis test. The student randomly picks one page from each of 25 of the company's instruction guides. And the teacher subjects the pages to a standard readability test. The reading levels of the 25 pages are given in the following table. Is there statistical evidence to support the teacher's belief? So our null hypothesis is that the mean is 6, and he's concerned that the reading level is higher. Now, what I could do is I could calculate a weighted average with 6 times 5, 10 times 6, 4 times 7, add all these up after I multiply them out and divide by 25. But it is much easier to do with the calculator. So first I'm going to go ahead and enter our data in a list. So I'm going to hit stat, edit, go into our list, and we have reading grade level. So we have grade 5, 6, 7, 8, 9, and 10. Then I put down how many pages I have of each. We have 6 at grade 5, 10 at grade 6, 4, 2, 2, and 1. Now if I wanted to, I could calculate statistics. I could go stat, calc, one bar stats, and make sure that I include the second list as my frequency list. Make sure second, and then stat to get the list, hit 2, and hit calculate. And then I would have my mean and my standard deviation for my sample, S of x, not sigma, by the way. And I could use that to run a t-test, right? So in fact, let's go ahead and do that. Stat, test. I'm going to do a t-test. And we had our stats, which I think it was 6 point. Oh, I need to go find out what they were. I didn't write them down. So let me go ahead and hit clear. Stat, calc, one of our stats, and then get that. So you want to write these down. 6.48, 1.39. 6.48, 1.39. So here we go, t-test. And we have stats. There's my 6.48. Oh, it remembered that. And our hypothesis is 6. Look at that. It actually pulled it in. It had 25. And our alternate hypothesis is that it's greater than 6. And then we could come down here. And I kind of like the draw because it gives me a pretty graph. And I get a p-value of 0.0483. Now, I could have skipped calculating one of our stats. I could have gone straight to stat test and t-test and then said, okay, I actually have data, and hit enter. And then you can see there's my 6, put list 1. For frequency list, I have to put list 2 because it tells me how many pages of each level I have. And then everything looks beautiful. And then we go and hit draw because I like the drawing. And voila, we get the same p-value of 0.0483. So we have the p-value of 0.0483, which means the p-value is between 0.01 and 0.05, which is indicating evidence for the teacher's belief. The correct answer is C. Number 9. A college admissions officer is interested in comparing the SAT math scores of high school applicants who have and who have not taken AP Stats. She randomly pulls a file of 5 applicants who took AP Stats and 5 who did not, and proceeds to run a t-test to compare the mean SAT math scores of the two groups. Which of the following is a necessary assumption? In other words, she needs this to proceed. All right. Basically, since we have such tiny samples, our population needs to be normally distributed. So the correct answer is D. So again, because of the very small sample sizes, we need a normal population for both. Number 10, suppose that among 6,000 students at a high school, 1,500 are taking honors courses and 1,800 prefer watching basketball to watching football. If taking honors courses and preferring basketball are independent, how many students are both taking honors courses and prefer basketball to football? So first of all, let's find out the probability someone's taking an honors course. It is 1,500 over 6,000 or 0.25. Now, what's the probability that someone is taking an honors course given they prefer basketball? So I'm looking for how many people prefer basketball and are taking an honors course. Well, if these two probabilities are independent, then the probability of honors given basketball should be the same as probability of just honors period, or 0.25. So I'm going to put a 0.25 there, multiply both sides by 1,800, and I get X is 450. Number 11, an inspection procedure at a manufacturing plant involves picking 3 items at random and then accepting the whole lot if at least 2 of the 3 items are in perfect condition. If in reality 90% of the whole lot are perfect, what is the probability that the lot will be accepted? So this is a binomial distribution with p equals 0.9 and n equals 3. We're going to accept the lot if we have 2 or 3 of the items are perfect, right? Not if it's just 0 or just 1. We need 2 successes or 3 successes. So we add the probabilities for both of those, and I'll use binom PDF, which is just the probability that X is 2, plus, and then go do binom PDF for the probability that X is 3. So to find binomial distributions, hit second bar, it's also distribution. You see it there in blue. And we have to scroll down a bit. It's easier actually to start on bottom. Now, since we're just doing 2 individual values, we're doing binom PDF. So for the first one, n is, oops, that's not what we wanted. Trials is 3, p is 0.9, and x is 2. And we get 0.243. Let's do it again for 3. PDF again, because we're doing individual values. So the only thing that changes this time is x is 3. So we have 3 out of 3. Add these 2 up. Oops. There we go. Enter, and you get 0.972. Now, an alternative way to do it is you could have said, well, it's just 1 minus the probability of 1 and lower. So you could have said, gone to binom CDF, oops, enter, put the 3 trials, P is 0.9, and we're subtracting out 0 and 1. And since it's CDF, it automatically starts at 0. Enter. And you get exactly the same answer. All right, number 12. Science majors in college pay an average of $650 per year for books with a standard deviation of $130, whereas English majors pay an average of $465 per year for books with a standard deviation of $90. What is the mean difference in standard deviation between the amounts paid for books by science and English majors? So the expected difference is the expected value for science minus the expected value for English. And we get $185, so we can see our options are B, C, or D. So we still need to go calculate standard deviation, and it's easier because we have 2 very different outcomes here. We have English and we have science, so those are different outcomes. So we're going to use variance instead of doing standard deviation directly. So we'll take variance of science, and then it's always a plus. We always add variances. I know you've asked me this before. So we'll do variance of science plus variance of English, even though that says minus. We never subtract variances, all right? So we get 130 squared, remember, as variance is the standard deviation squared, and 90 squared for English, or 25,000. Then we are going to find the standard deviation. We just take the square root of our variance, and we get $158.11, which is basically choice C. Number 13, city planners are trying to decide among various parking plan options ranging from more on-street spaces to multi-level facilities to spread out small lots. Before making a decision, they wish to test the downtown merchants' claim that the shoppers park for an average of only 47 minutes in the downtown area. The planners have decided to tabulate parking durations for 225 shoppers and to reject the merchant's claim if the sample mean exceeds 50 minutes. If the merchant's claim is wrong and the true mean is 51 minutes, what is the probability that the random sample will lead to a type 2 error? That is, the mistaken failure to reject the merchant's claim. And we're going to assume that the standard deviation in parking durations is 27 minutes. So the true values are 51 minutes, 27 minutes for standard deviation, and we're going to take a sample size of 225. Our null is that it's 47 minutes, and our alternate is that it's more than 47. We'll reject H naught if X bar, if our mean value is greater than 50, right? Because he said if he exceeds 50 minutes. But so that would be the correct decision since we know the true value is 51. Type 2 error occurs when we fail to reject H naught because we don't change our mind that it is greater than 47. So we got to figure out the probability that we're going to get 50 or less on our sample average to figure out the probability of a type 2 error. So I have my standardized test statistics since these are all written in test statistic format. And our statistic from our sample would be 50. Our parameter, our true value is 51, right? And then standard error is just going to be 27 over square root of 225, right? And that works out to choice C. Number 14, which of the following is a true statement about hypothesis testing? So I went ahead and added this drawing to help with number A. So if there's sufficient evidence to reject a null hypothesis at the 10% level, then there is sufficient evidence to reject it at the 5% level. So when we reject at 10%, we have a higher rejection area. So this starting at Z is 1.2816 and up, that would all be rejection for an alpha of 10%. Whereas if we're doing an alpha of 5%, we would reject at 1.645 and up. So this is false because Z could be anywhere between these two for all we know, in which case we would reject for 10%, but not for 5%. Okay, whether to use a one-sided, so A is false. B, whether to use a one or a two-sided test is typically decided after the data are gathered. That is false. Otherwise, we would never have two-sided tests because your data is only going to be on one side. So you always have to decide beforehand, are you doing a one-sided or a two-sided, and then use the data to decide. C, if a hypothesis test is conducted at the 1% level, there's a 1% chance of rejecting the null hypothesis. This is only true if the null is actually true, all right? If the null is not true, then the probability of rejection is higher because the true value is actually further away, okay? So C is false. D, the probability of a type 1 error plus the probability of a type 2 error always equal 1. That is also false. If the probability of a type 1 is not 0, then the probability, so in other words, you could have a type 1 error. Let's say you set alpha at 0.05. So that means the null is true. That means the alternate is false, and there's no way to make a type 2 error because the alternate is not true. And you could go vice versa. If the alternate's true, you can make a type 2 error, but you can't make a type 1 error. Then finally, the power of a test concerns its ability to detect an alternative hypothesis. That is 100% true.